Hi, I'm Meg Schwam. I'm an assistant scientist at Gemini Observatory, and this week I'm a recipient, or one of the recipients, of the American Astronomical Society's Division of Planetary Sciences Carl Sagan Medal. And as part of that, I'm going to be giving a public talk in Provo, Utah at the Division of Planetary Sciences meeting. And one of the ways I thought I could share this moment with more people and share this public talk with more people is by recording it, one of my run-throughs, and putting that online. So this is a version of a very similar version of what I'm going to be giving in Utah tomorrow. So I'm going to be talking about exploring Mars with 150,000 Earthlings, and I really do mean 150,000 people. My research has been involving the public to explore the surface of Mars using online citizen science and human pattern recognition. But if we want to take just a step back and sort of think of Mars in sort of a global context, why do we want to study Mars? Why is Mars interesting? Well, Mars at some point, we think in the past, had a thicker atmosphere, had some standing water somewhere in parts of the surface. And so there's a lot that we can understand about Mars's evolution history and how it's different from the Earth. That's important for giving us better context for our own planet. And then also just studying planet formation in general and the evolution of planets by understanding how Mars went from, if we think, a thicker atmosphere and water on the surface to the sort of very dry and arid and cold place that exists today. And I think when you think of Mars, or at least when I think of Mars, one of the first images I think of is Curiosity. The selfie-taking rover roaming around doing geology on the surface of Mars. And this is one of the selfies from Curiosity. And Curiosity is doing a lot of great science, and it's trying to help us understand how Mars at some point was Earth-like, and telling us that story of water. But what I'm really interested in, I think, is really important to understand as well, is how is Mars different than Earth? And one of the ways it's very different is when you look at the polar caps. So this is an image of the South Polar cap, and this is different from our caps on our poles on Earth because these are made of carbon dioxide ice. So unlike water ice, these sublimate and turn straight from solid ice to gas. And so we don't have this on the Earth. We don't have standing deposits of carbon dioxide ice. And another really important thing is that in the current Martian atmosphere, about 20% in terms of mass of the atmosphere condenses out each winter to form this southern ice cap, temporary ice cap. And so that's a lot of mass in the atmosphere that's coming out and condensing out into this seasonal ice cap. And that in the spring and summer, that ice cap sublimates back into gas and moves towards the northern pole that's now in winter and deposited there. And so understanding that process is very different from what we have on Earth. And the other thing is that if you look at the seasonal ice cap, during that spring, southern spring, what you notice and start to see if you're looking from orbit, and this is an image from HiRISE, one of the cameras aboard Mars Reconnaissance Orbiter, you see these beautiful dark fans and sort of blotch-like features on the surface. And what we think these are, we actually think they're the result of carbon dioxide jets coming from that sublimating seasonal ice sheet. So here's an artist rendition of what we think. I would definitely not want to be standing on the surface of Mars on the South Polar ice sheet when this is going on. I bet it's pretty loud and you're hearing ice cracking. And what we think is happening is that the sunlight is penetrating through this seasonal ice cap that's only about a meter thick, and that the sunlight penetrates through, heating the soil, and that you get a layer of trapped carbon dioxide gas. And that gas breaks through in any way it can to get back to the atmosphere to equilibrate and brings dust and dirt with it. And we think that these don't go very high, maybe a story, maybe not much more than that, and sort of because we don't see from orbit sort of these shadows from the plume sort of turning over, so we think that these are pretty low to the ground. And it's the local surface winds sort of blowing the material into those beautiful fans. So this is another view of that, sort of showing that in the bottom picture, again, that the seasonal ice cap has the sun penetrate through, you sublimate that layer of gas between the base of the ice sheet and the soil, and then it breaks through, bringing up that material. And so on the top view is an image of HiRISE of the same spot from spring to mid-spring to early summer. And one of the things that we know, and that we think this is hypothesis is on the right track, is that In the spring, we can see spectrally the signature of carbon dioxide ice. The surface is at the temperature of carbon dioxide ice, and that you start seeing these beautiful dark fans. And then by summer, those fans disappear when we know there's no carbon dioxide ice. So why do they look dark? Well, we think that's because the ice sheet is not completely translucent. It's semi-translucent. So you can think of it like looking through a piece of frosted glass. And so when that atmosphere condenses out and possibly snows out and to form that carbon dioxide ice sheet, mixed into that is that red atmospheric dust, that red rust that makes Mars red is embedded in that, is in that ice sheet. And so when you have the dust and soil from below coming up and land on top of the ice sheet, just like if you had a piece of frosted glass and I take something and I move it from the top to below it, they look a little different because you've got that opacity. And so those seasonal fans look dark when you're on top of that seasonal ice sheet, and that when that ice sheet disappears, you see almost see no difference because the fan particles sink back down and blend right in. And what you might also notice if you see that there's this sort of pit with these radiating channels in these images. And what we think those are, and they've been nicknamed spiders here because they really do look like a pit with legs, or the formal name for them are araneiforms, Latin for spider. So nobody gets confused about there being life on Mars. These are not real spiders. They're not real insects. But that these are the channels that are carved over eons from this sort of cyclical process of there being carbon dioxide jet and sort of bringing up material from the same point and then distributing it to the surface and moving it somewhere else. And so we see these channels sort of, we think, carved over or eons from this process. Now we do see seasonal fans where we don't see these channels, but where we tend to see these channels, we tend to see above them emanating from sort of a point nearby these seasonal fans. So we think they're related. And just to show you a schematic of that, I think to show how we think those, in a sort of sped up way, you're seeing these channels being carved. This is in the Kelso Dunes, and on a hot day, a piece of carbon dioxide ice has been put down, and you can sort of see at the edges how it's moving that material around. And so we think over time it's sort of eroding through that surface. So why do we care about these seasonal fans? What makes them interesting? Well, a couple of reasons. One, they're really important because they're the way we're turning carbon dioxide to the atmosphere through this jet process. So if we can understand the seasonal fans and actually measure their shapes and their area, we actually can estimate, because we know roughly the particle size, how much carbon dioxide was outgassed. And so we can see how that changes from over time or from season to season on the South Pole, which is interesting. The other thing is that these fans, as I said before, we think are being blown by the seasonal wind, the local surface seasonal winds. And so, as you can see here in this image where we see wind, that it looks like these fans are sort of bifurcating and looks like there's two directions, like the wind direction changed. Well, if we can measure these and map these, we can actually get a wind measurement on the surface of Mars. And we think on the other side, where we see these more sort of elliptical features, we even call them sometimes blotches, it's really just where you're getting that sort of outgassing from the jet, sort of coming up and then the plume coming back down right where the vent is. And so if you can map where you don't see these fans, then that's telling you the wind's not strong enough or not blowing to produce these seasonal fans. And then where you do see seasonal fans, you can get the wind strength and direction from the length and direction of these fans. And that's really important because the wind direct measurements we have for Mars are from things we've sent to the surface. So the rovers, landers have had, plumb bobs and other anemometers and other ways of measuring the wind. And so we have a few points scattered on the surface. But if we can measure all these different sort of wind directions, and there's hundreds of thousands of these fans just even in the small number of images we have, we could make the largest wind map on Mars. And the reason why that's important is because we want to understand Mars's past history. We want to look at climate models and see how they behave and how the atmosphere works by putting all the physics that we know about atmospheres into the model, computer model, and letting it run, knowing what we know about Mars. And the boundary layer sort of between the surface and the atmosphere is a really tough to get right. And so we can want to check for these models by seeing how well they reproduce these wind measurements that we do get for the South Pole. And then they're also important because we can use them as input to better improve these models. So if we want to turn back the clock, you need to get Mars right now. And so understanding if we can get Mars, a better representation of Mars now, that's important for understanding its climate, and understanding how seasonal processes and change work on the South Pole. And what's great about the HiRISE camera, which is the highest resolution camera we've ever sent to Mars, you can see about a coffee table sized object on the surface is about its resolution capability. It's been orbiting Mars for 10 years on Mars Reconnaissance Orbiter. So that's 10 Earth years, so it turns into 5 Mars years because Mars is in a larger orbit compared to Earth. So it takes about 2 Earth years for Mars to orbit the sun. So HiRISE has been imaging many of these different regions dotted in blue on the surface of Mars, on the South Pole. And so we have all these beautiful fan observations, tens of thousands of fans in these, thousands and hundreds of thousands of these fans in these images. And so if we could map these shapes and sizes and wind directions, we could make this wind map and start to understand these processes. And it's not just over one Mars season. Because we have these multiple seasons, we can see how different things in the Martian atmosphere impact this process of the carbon dioxide sheet sublimating from the base, creating these jets and creating these seasonal fans. And so here's just one spot from season 1 of a HiRISE campaign when the mission arrived in 2007, I believe. And then this is season 2, so it's roughly two Earth years later, so 1 Mars year later, at the same spot. Now, the difference you might notice immediately between these two, that there's a lot more fans showing up in season 2. Now, these are roughly the same time of year, same kind of solar insolation, but what's different is that between season 1 and season 2, when this ice sheet was forming, when the South Pole was shrouded in darkness and it was snowing carbon dioxide ice, there was a global dust storm that obscured the surface of Mars, and there was worry that the rovers would not have enough power to survive because they couldn't see the sun. The rovers were Opportunity and Spirit. Those were the 2 rovers at the time. They're okay. Well, they made it through that. Spirit has stopped functioning, but it lived a very happy life after this dust storm. But what's exciting is that that dust storm left its imprint in that ice sheet. Because, as I said, some of that atmospheric dust condenses out with the carbon dioxide ice to form that ice sheet. And so we know there's more atmospheric dust in this ice sheet. And so trying to understand what does that do to this carbon dioxide jet process, and how does it speed it up, does it slow it down, how long does it take for the Martian atmosphere to rebound back to where it was at season 1, we can try to study by measuring and mapping the number of fans over time in each of these monitoring seasons. And we can also see not from just year to year, Mars year to Mars year, but also throughout a single Mars year, going from early spring on the South Pole all the way through summer when the carbon dioxide is completely sublimated. This is showing a HiRISE snapshot of basically the same region, and you can just see how these blotches and fans sort of pop up and appear and disappear and change shape over several different sort of epochs in one HiRISE monitoring campaign season. So if we can both really understand a lot about Mars's climate, both on a sort of interannual timescale, but also sort of, again, within a single sort of different seasons within the same Mars year. So I hope I've sort of driven the point home why it'd be really nice to get all these fan measurements. But one of the problems has been, how do I map these? And this is just showing a smattering of different HiRISE images of the South Pole. These are roughly colors, so roughly what you would see if you're looking at the surface. It's a little bit different, but pretty close approximation. And you can see, just like Earth, there are varied colors and textures and surfaces. And on top of that, I think in some of these images you can see sort of the dark splotches where the seasonal fans are. So while I'm rattling on, you're probably already noticing which images don't have anything in it, like and which ones do. And so the problem my collaborators and I found was that it was really hard to get machines to do this, to identify where these seasonal fans were and to map them. And getting the edges of these shapes right, because these are dark features that are sort of gradually sort of degrading, and it's hard to understand where that fuzzy boundary is, but your eye is very easily able to do this. And so the point being is that if we could get people to help us with this task, we'd be able to map these seasonal fans. And with the internet, we can connect people and to help us do this. So, and the average American is on Facebook for about half an hour every day. And if you could tap into just a small amount of that time, we could get this project done. And so that's really what we set out to do, to use citizen science and human pattern recognition through the internet to be able to help map these seasonal fans and enlist the public in exploring Mars. And because we have the internet, anyone with a browser can do this, because this is really the innate pattern recognition skills that our brains have learned over evolution and time to be able to do. And so these are the innate things that we know how to do. Just like babies are able to recognize faces of their mother and family, it's really hard to make machines do that. And I just flew from New Zealand last week, and as I was exiting the country, their automatic gates with facial recognition failed to figure out that I was my passport image. So we're still not 100% there at getting machines to identify features, but human beings innately know, in most cases, our friends and family just by seeing their faces in a crowd. And so it's really easy for us to pick out patterns. It's really easy for us to pick out things the outliers, a thing that doesn't belong, in patterns and other things. And so if we can tap into this potential, we could solve this problem and many other problems that we're having in data analysis, where it's hard to automate, or it's too challenging or difficult to do with machines, or we want to be able to check what the machines are doing and see what things might be lost by doing it with an automated method. So this is what the Zooniverse has been built for. So the Zooniverse is a platform where you can go, if you're a scientist, and enlist the public, build a project and enlist the public in helping you identify and mark features and images and other sort of data analysis tasks that are hard to get computers to do. So if you hate Mars, or you're not interested in mapping seasonal fans, go to zooniverse.org and you can count penguins. Who doesn't want to count penguins? Or identify animals and camera traps in the Serengeti. And these are actually all helping scientists do real analysis and real science with this data. And so when you go to a Zooniverse project, you are contributing to science, and you are actually helping a scientist like me be able to do tasks and analysis tasks that are hard for us to do without having the help of the public. So you can go to zooniverse.org and dive in. So if you get bored of my talk, you can also just go to zooniverse.org. There's a whole bunch of projects that work on your mobile phone. So if you get bored, you can start counting penguins right away. Trust me, I won't be upset. So you can go ahead to zooniverse.org right now, or go later. But what I want to tell you about is Planet 4 and our other project, Planet 4 Terrains. So we linked with the Zooniverse to build Planet 4 to enlist the public to help us to look for these seasonal fans and map them. And so just to give you a precursor, you can go to planet4.org, and with your browser, you can go and we ask you, after a simple tutorial, to go mark where you see these seasonal fans with an ice cream tool, and then we use an ellipse to mark blotches. And so you see a quick tutorial and you're off to the races, and that's all you need. All you need is a web browser to be able to contribute to the Planet 4 project. And we have 20 people look at each one of these images, because it's really that wisdom of crowds. It's the assessment of many non-experts together that outperforms machine learning and many computer algorithms. And so, and often outperforms inconsistency to the experts, because it's going to depend on how much coffee I've had and how much sleep I had about whether, how accurately I can identify fans and blotches and images that I see. But if we have several people doing it together and combining the results, we get a much more consistent answer. And so that's what we're doing for Planet 4. We have tons of images on the site that we're in need of help looking, and so you can look at them today. And so I wanted to talk a little bit about the results from Planet 4 and how do we actually combine the data, because that's great that we're doing this, but how do we actually get through it? Well, so here's actually showing some of the data. So this is an image from Planet 4. The individual markings in the first blank are the individual users who marked, and you can see in their different colors mean different classifiers. And so you can see there's one person who put that big circle, so maybe not did the task necessarily as in the way we interpret it, of marking each individual ones. But you can see by combining those multiple classifications together, at the end state, when we have those individual sort of remaining features in those different colors, we really do identify those fans and blotches. Here's another way of showing that. These are actually several of these Planet 4 images from HiRISE or subtiles. We cut the HiRISE images from larger images into smaller. So these are actually 6 Planet 4 images put together, and you can see the different colors or the different sort of tiles or subframes that were classified by different users. And so we had each of these frames had 20 people looking at the images, and so you can see we really do reproduce the fans and blotches that are seen in this image. I think we're doing pretty well in identifying the catalog. And so we are using people and enlisting the public to help us and come along this journey to study the South Pole of Mars and study these seasonal processes. So now that we have this clustering algorithm, we just finalized in the last few weeks our algorithm, and so we are now producing the final catalog and writing the first paper from Planet 4. So we're now starting to get these wind directions that we can start comparing to these climate models and to other things like that. So I want to switch gears and talk about how Planet 4 sort of spawned another citizen science project, Planet 4 Terrains, and how we were able to, with the public, sort of commandeer a NASA spacecraft and point at new locations. So when the Zooniverse launched their new platform 2 years ago, they asked us if we would like to launch new projects as part of that. And one of the things we thought about was, we're studying the same regions with Planet 4 because HiRISE has been orbiting Mars for 10 years with Mars Reconnaissance Orbiter and has been really basically imaging roughly these same blue areas from time to time. And the thought that we came up with was, well, with Planet 4, we're looking at these fan directions. What about if we looked for new areas where we know there's seasonal activity and seasonal fans and compare that with what we're seeing from the regions we've already studied for 5 Mars years? And so one of the thoughts we had is that although the seasonal fans might be hard to see because they can cover the surface depending on the image resolution you have, you can see the spiders. And so if you look for these spiders or Aranea forms, where we know that they are, there's jet activity. So if we can find the spiders in ice-free images, then we can sort of find these features and then come back in the spring and image them and do monitoring campaigns like we've done in other parts of the South Pole and compare those seasonal fans and their distributions of wind directions by putting those images through Planet 4 to get that information. So that's what we did. So instead of using HiRISE, we used CTX, which is the context camera for HiRISE. So HiRISE is so high resolution, it actually has its own camera to tell you, sort of give you the picture of where you are on Mars that you're imaging. So context camera actually has lower resolution, spatial resolution, but it covers a wider swath. So it's ideal for our search because every time that Mars Reconnaissance Orbiter images or takes spectral data, CTX, the context camera, goes up to give context to those images, and so we can use that data to study the South, to study where we think these RNA forms are and have people look at them and find these in the images, and then we can target. And so just to show you these spiders at CTX resolution, here they are. I think you can see a pit with sort of legs coming from them in this image here. And so that's what we did. We searched 90 CTX images spread over all of the sort of a good chunk of the South Pole, 11% of the surface within minus 75 degrees. And the point being is that we wanted to sort of get good coverage of these features. So here's Planet 4 Terrains, the new this project. So we'd show a subframe from CTX and we ask you what you see in the image, and I'll go through that in 1 second. So we've had over 14,000 volunteers in this project, contributing over 70,000 classifications. So we asked people to look for spiders. So again, that pit with legs. We asked them to form baby spiders. So we're basically breaking these Aranea forms into their different types. They're basically spiders without legs or spiders with legs that are really tiny compared to the body. So we're being qualitative here, not quantitative, but that's kind of what we're looking for. And then in channel networks, we're looking for these Aranea forms that have sort of these interconnected legs together, and there's not really a central pit. So that's what we call channel networks. And we also had people identify Swiss cheese terrain. These are because it's kind of striking in the images. I think it looks like Swiss cheese. And these are, I didn't give the name, this has been given by other people who have looked at images many years ago when orbiters have been imaging this region. And so this is actually on the permanent ice cap where there's carbon dioxide ice. This is due to the uneven sublimation and deposition of carbon dioxide ice over the multiple seasons on the South Pole. So we thought that this is striking enough that we wanted people to mark it because they'd probably note it as in the images. And then also we thought it'd be a good idea at some point we might want to identify craters, and that there are people in the high-rise team interested in how craters evolve in icy soil, and so that this would be a good way we could get a sample. So this is the interface. We asked you to look at the image and then mark down where you think you see, what features you see. But I also want to mention that part of this, we also have a discussion tool, and this discussion tool is basically Facebook for data on the Zooniverse platform. And it's great because it enables serendipity. So I just want to mention the sense that if there's features that you build your interface for, what about the things you didn't expect to find? By having so many people looking through the data, they find those rare jewels. Well, by having this discussion tool, people can comment and discuss what images they're seeing and find things that you might not be looking for. So in this case, Ray Perry, one of the volunteers on the site, sort of noticed in this image, and he says, a nursery, lovely, well-formed spiders together with baby spiders and partly developed spiders. And in this case, you can sort of see it goes from these baby spiders to then we see these full spiders with legs, and then the channel networks. Well, in the main interface, we wouldn't actually have we would have, you click all those buttons, but it wouldn't tell me about how they're distributed. And so it's kind of neat that we're seeing this sort of evolution. And so this is actually one of the regions that we targeted with high-rise to study more about because of getting Ray Perry's comment. So by the Zooniverse building this discussion tool, we're able to tap into this serendipity and tap into those discoveries we might not have expected to find. So I just wanted to mention that in all Zooniverse projects, for the most part, have this discussion tool where volunteers can directly interact with the science teams and other people involved in the project. So what did we find with Planet for Terrains? Well, we had a year when we sort of thought up this project to when southern spring was going to arrive on the South Pole. So we had about a year to come up with a new set of targets to look at. If we had tried to do this with the research team ourselves, we wouldn't have made it. But by having so many people helping us, we were actually able to identify 20 new high-rise targets that were part of the seasonal campaign. I like to say that the public commandeered a spacecraft they paid for with tax money to study the South Pole. So this is actually one of the images of one of the regions that they found. This is another image showing the CTX image where we identified these spiders, and then you can see in the next image, this is from high-rise, the high-rise campaign, you can see those dark seasonal fans. So again, telling us that we really are seeing these jet activities, we really are seeing Aranea forms of these spiders. And here's a distribution of these spiders on a geologic map. So the magenta are the detections from Planet 4 terrains, the identifications that our volunteers found. And one of the really interesting things that we found was we find spiders where they're not supposed to be. So we expected Aranea forms to be in this blue region, which is called the subpolar layer deposits. That's because it's this sort of conglomeration of ice and dust that has water, ice, and dust that has formed over time in a cyclic manner. And the top of the layer is very loosely conglomerated. And the thought was that from past searches, they'd all found spiders to be in this blue unit in the South Polar deposit. And the thought was just that this soil was very loosely conglomerated, and that's why these things were there. But if you look at our map, we clearly have these Aranea forms on locations that are outside of this layer. And so we imaged with high-rise to see whether or not these are actually real and whether these are new locations for Aranea forms, and that the carbon dioxide jet process is happening outside of the South Polar deposits and is actively carving, or at some point had carved, these channels into the surface. And so these are images from high-rise of some of these locations outside of the South Polar deposits, and we clearly see these wiggly dendritic channels that are the indication of having of Aranea forms, and we see those beautiful dark streaks that are telling us that there are seasonal fans and carbon dioxide jet activity. So I'll just show you another few images. Again, this is gouges with spiders, spider legs coming off of it. Here's another region. Again, we sort of see these spider-like legs with the seasonal fans, in another region where we see, again, these spiders with these seasonal fans. So we were supposed to end Planet 4 terrains. After a year, we were going to get these new targets, feed them back to Planet 4, and that was going to be it. And because we now know that there are these seasonal fans and carbon dioxide jets having, at least at some point in the past, or actively carving the surface in different areas that are not in the subpolar deposits, we are continuing the search. And so we're making more work for ourselves by continuing on Planet for Terrains, because the public has helped us discover something new and interesting about the South Pole of Mars. And so we have added new data to the site. We are expanding out further so we can see how far do these RNA-informed features may extend out on the seasonal ice cap in terms of latitude, which is important for missions. If we ever want to send another mission to the South Pole or the South Polar region, it'd be good to know where these things are distributed. And the other thing is that we have a working hypothesis that we think that possibly where we're seeing these new RNA-form features are possibly where we've seen upheaval of the soil from impact craters, and that we're looking at ejecta blankets from the material coming back down after it's been excavated from an impact in the soil. And so we can study that more if we can find more of these RNA forms outside the South Polar deposits, and we're actively looking for them now. We have some new targets that we're going to be hopefully imaging HiRISE when we get back to the South Polar, get back to the summer. So I just want to end by thanking and acknowledging the people that make these projects happen. So it's not just me, it's these people as well, from the Zooniverse team to the Planetary Science team. So I just want to take a moment to acknowledge them, as well as the 150,000 people who have made both Planet 4 and Planet 4 Terrains work, because without them, this wouldn't happen. So I'll leave up the websites for the projects, for our Mars project in the Zooniverse, and really just say that it's with the public and the people of Earth that we're studying the red planet and learning more about our next door neighbor.